Thanks everyone. So as you can tell from the talk, we're talking about GPS positioning and trying to make it more accurate while it's affordable. The very accurate GPS systems are available. If you've got enough money, you can get GPS positioning down to the centimetre level, or if you've got even more money, possibly down to the millimetre level. And although usually that's a very static situation, we don't have that sort of money, and we'd like to build systems that's available to the community for anyone who wants to be able to do good positioning. So we started exploring ways to get more accurate GPS positioning on the cheap, both in terms of dollar cost and in terms of computational power required in the vehicle that you're trying to position. So Ben Nizette is working on a project on positioning at the Australian National University and in Canberra, and I'm in Canberra as well, and I started writing an implementation of a differential GPS system, and then Ben stumbled across my work, and we've been collaborating for the last year or so on and off on trying to make the system work. So towards the end we'll give a bit of a demo, and we've done some positioning here at UWA on the James Oval just outside this theatre, and we'll show the results of that, but we'll talk a bit about the theory of how it all works first of all. So why do we want to do it? Well, basically we want to get accurate positioning for little vehicles like this. This is a autonomous rover running the APM rover code. This has got a pre-release version of the Pixhawk autopilot on it, and it's got a couple of GPSs. The idea of having the two GPSs is we have one of them differentially corrected using our code, and one of them not differentially corrected, and we feed both results through the autopilot into the logs into the ground station, and we can then tell whether we've made any difference at all to the system, because we want to actually know that it is better than not doing corrections. Ben's motivation was primarily sort of swarms of copters. He wants to be able to have swarms of quadcopters flying in formation, and you need very good relative positioning between those copters, because if you don't, what happens? They run into each other, and then that's bad because you have to rebuild the copters, etc. So I'm interested in it from search and rescue systems for UAVs, accurate landing, accurate georeferencing of images taken from the aircraft. Also want to improve the velocity values that we get out of GPSs, because that's important for accurate attitude, knowing which way is up. You use the velocity numbers from the GPS to correct your the accelerometers in getting the correct attitude in an aircraft. So that's the motivation. Thought I'd very briefly cover how GPS works. I'm guessing most of you already know. Most geeks would have read up at least at the Wikipedia level how GPS works. So I'll go over this fairly quickly. As it was mentioned in the introduction, we're very happy to answer questions during the talk. So if you have any questions about what we're doing, or if we're not going into enough detail, then please ask. You can of course also read the code later, the URL for a GitHub project with all of our code. Basically, simple explanation of GPS is that it's clocks in the sky. So there's these space vehicles, satellites that have accurate clocks on board them, and or at least they know what the inaccuracies of their clocks are, rather than actually being accurate, and they are able to not only announce the time, but what they think is wrong with their time, and announce that from the clocks down to the ground. And a GPS receiver, such as these little cheap GPS receivers here, can pick up those signals with amazingly sensitive, it's an incredibly weak signal when it arrives on the ground, but these are amazing little devices that are able to pick that signal out of the noise, and then they basically triangulate. Now, the triangulation, something I didn't realise when I started this project, I always thought the triangulation in GPSs was three-dimensional, just the coordinates, the Earth ECEF coordinates, basically, meters from the centre of the Earth type thing. It's actually in 4 dimensions. You're triangulating over time as well. And that's because when you have a cheap GPS like we have here, they have fairly bad clocks on them, right? The clocks on these things are not good enough to get accurate positioning. So what you do is you actually, in doing your least squares triangulation, one of the dimensions of that is to work out what your own clock error is, and the reason that's possible is that clock error contributes, it's a common mode error, contributes to the error from all of the satellites, therefore you can eliminate it because you have, 6, 8 satellites or whatever, so you can eliminate common mode stuff like that by doing least squares positioning. So that gets you, you can do more accurate positioning by tracking carrier phase, so that's basically tracking the actual waveform, the sort of the 19 centimetre waveform, and these receivers are capable of doing some degree of carrier phase tracking, and some of the receivers we've got here, such as this one here, which is a U-Block 6T, and this one here, which is a U-Block 6P, they're capable of not only tracking that carrier phase, but telling you what the result of that tracking is across the serial interface, so you can get some phase information out of the receiver, which is very useful for the stuff that we're doing. Okay, the problem with, of course, tracking carrier phase is you can work out what your position is to, along that 19 centimetre waveform, but you don't know which waveform it is. So you have an integer ambiguity where you can say you're precisely to that centimetre, but you've no idea how many 19 centimetre units you've got. And that's one of the challenges with GPS, is that disambiguation of those multiples. Okay, so that's basics GPS, and I realise that I've glossed over a lot of details there. There's all sorts of, stuff with relativistic effects and all sorts of things you have to take into account. I've always thought it's cool that GPSs are one of the demonstrations that Einstein was right about special relativity. It's great, and if you don't take that into account, your position is off between 20 and 30 metres. And so, it's a great demo. Okay, so how accurate is GPS? Well, it depends on how much you spend, where you live, and how much CPU power you've got. So how much you spend is a very big factor. Base GPS modules, like these little ones here, in Australia, will give you a positioning error of the order of 10 metres, often quite a bit less. One of the curses we've had with some of our testing is we've sometimes had good GPS days, where an uncorrected normal GPS gives us a position to within 1 or 2 metres for the hours of testing, and we're frustrated at those damn satellites being so good because we want it to be rotten so that our corrected system can improve it, right? So luckily here in Perth we got a little bit worse time for a while, and we were able to get a better demonstration. Those GPS type modules are sort of $50 or so of that order. They can get them for $20 cheaply at some places, but these are retail prices for a complete module, ready to plug into a serial port. In the US, Europe and Japan and some other places in the world, you can reduce the error to of the order of 3 metre type errors, because they've got satellite-based augmentation system, which essentially means the satellites, some additional satellites, provide extra signals which provide similar corrections to what we're trying to do in our project directly from the satellite, and your receiver is able to interpret those additional corrections and improve the signal, improve the results. Dual frequency GPS receivers can do a lot better. Anyone tell me why dual frequency is so much? So these are single frequency receivers. They basically receive on the primary 1.5 gigahertz frequency.
You can calculate the ionospheric.
Exactly, yes. One of the primary sources of error. Yep.
And at the L2 frequency, it has different chipping rate.
Yeah. So it has more information available. That's right. So the L2 frequency, dual frequency ones, both has more and better information encoded in the signal, as well as giving the two frequencies, those two frequencies are different dispersion rates, I guess it is, in the ionosphere. And from the difference between the two, you can get a much better estimate of what is happening in the ionosphere with the signals coming from the satellite to the Earth. And so that better estimation allows you to correct for it a lot better. So dual frequency, good. Unfortunately, dual frequency, expensive. There are no really cheap dual frequency receivers. If you know of one, please let us know. Yeah?
Very briefly, a couple of months ago, somebody was talking about using a DGPS receiver.
Yes.
Hacking the firmware, or basically completely disregarding it.
Yes.
And using that to listen relatively.
Yes. I have tried that. The sensitivity doesn't seem to be great on those, not at the levels we want. It is possible. It was a fantastic demo, and I loved that and that it could work.
But in theory, then you can listen to whatever you want.
Yes, that's right. That's right. And maybe when those SDR type receivers, get to the level of sensitivity, but I suspect it's the RF stages that, they're really highly tuned for GPSs, and the correlators are very highly specialized. They were talking in that demonstration, picking up the signal over many, many hours before they even get lock, and it wasn't the sort of, turn it on a minute later, you have your position. But it may well advance, and that is an exciting, prospect of using SDR type techniques to improve upon GPS. There's other prospects as well. If you guys have heard of the Pixie and the SwiftNav Pixie, which is an open source GPS with an STM32 on it. That's also very interesting and may offer some possibilities of doing slightly more specialized open source GPSs. We'll talk about that a bit more later.
Could you repeat the question because it doesn't.
Oh yes, repeat the question. So the question was about using software-defined radios to get the possibility of doing dual frequency on the cheap by using something like a software-defined radio to allow you to listen onto multiple frequencies. And I agree that that's a really exciting proposition. As yet, it's not quite there. Much of the stuff we're doing may well be obsoleted by next week. So with a source of corrections and dual frequency, people talk about getting decimeter type accuracy, 10 centimeters type accuracy. And with really great corrections and a $10,000 receiver, you can get down to being survey quality type stuff, centimeter level. With the sort of gear that Geoscience Australia has, they can talk about getting millimeter type level precision. It also depends how much CPU power you have. Many of you would know about RTK-lib, which is a great project from a open source developer in Japan. And there's other open source GPS and RTK implementations. RTK is real-time kinematic, which basically does the maths related to that disambiguation of that integer ambiguity with the carrier phase. And it's a great solution, but it requires you have substantial CPU power at the moment in the aircraft. And we're trying to have solutions that scale to dozens of quadcopters, all very cheap, having really cheap GPSs on each of the vehicles and not having to have more expensive computing equipment on each of the vehicles. So that's something that it's interesting to look into, but isn't within the scope of our particular project. Okay, sources of GPS error. So why do things go wrong? You get mismatch between the ionospheric model and the actual atmospheric conditions. So they have, in these sort of GPSs, relatively simplistic atmospheric models. And of course, the ionosphere is a very changeable thing. And so the signals as coming through the ionosphere get different delays depending on what the sun is doing, depending on the time of day, the weather, the humidity at some levels of the atmosphere can affect the dispersion of the signal in the atmosphere. If you've got a mismatch in the model, then the corrections you do for the signal travel time through the ionosphere can be poor, and that is the biggest source of errors, apart from probably bugs in the code. That's probably the other really big source of errors, both in our code and receivers and other receivers. Multipathing is a huge one, where signals bounce off another surface and don't come direct to the receiver. Enormous source of errors, very difficult to deal with, and it's caused us a lot of issues. Luckily, once the aircraft is up at 100 or 200 meters in the air, multipathing isn't such a problem. But for a ground vehicle like this, multipathing can be a major issue. Dynamic model mismatch to real movement. The GPSs don't just solve the geometric problem on a per packet basis. They've got little dynamic models, little Kalman filters and similar built into them where they're trying to model the trajectory of the vehicle, and there can be limitations to those dynamic models that don't match the actual physics of how the vehicle can move, and that can cause significant errors which can extend over long periods of time. Particularly if you've got a rocket going at 100 G, as we have in the audience. Tropospheric errors are smaller, but you also get significant errors in the modelling of the signals in the troposphere. Antenna errors usually are much smaller. These are roughly in order of magnitude. Clock errors, both the errors in the estimation of the clock error in the satellites and clock errors on the ground, although you should be able to get rid of those as they're common mode. errors, and orbital errors can be interesting, where you might have to, you got bad estimates of what the orbit of the satellite is, because you really need to know where the satellite is, otherwise you can't solve the geometric problem of where you are. And so that's encoded in something called the ephemeris that it broadcasts down periodically. If there's errors in that information, then that can give a poor positioning. So there's lots of other sources of errors, but these are the most common and best known ones. Okay, so what is differential GPS? So the major errors are spatially correlated. So in other words, the errors you get on a receiver here and the error you get on a receiver a few kilometres away, the biggest errors are highly correlated between the two, right? So if you can measure the errors at one spot, you can transmit what errors you've got, if you can work out what the errors actually are at one position, to the GPS receiver at the other position, and ask it to apply corrections to its solution based on the errors that you've got. You have to do this per satellite. You can't do it as an overall position error, but for each satellite, you can work out what the error in the path estimate, the geometric distance is to each satellite at a ground station, and then send that to the other GPS. That's differential GPS in a nutshell. So the steps you use, you need a reference station to measure the error. That reference station can be one that you provide, for example, something like this connected to your laptop. It can be something provided by another satellite. That's what SBAS does. It can be something provided by a government authority, like Geoscience Australia provides corrections at locations around Australia, and luckily there's one quite close to us, about 19 kilometres away in Perth, and there's ones close to us in Canberra. And so if you've got access to that, you can do corrections. It assumes you know the true position of the reference station, and that's one of the hardest problems. Unless you only want relative positioning, then you don't need to know the real true position of the reference station. But if you want absolute global positioning, you need to know where the reference station is. It's really difficult to get that sometimes. You then send the measured errors for each satellite to the rover, and the rover is a generic term, it could be an aerial vehicle or a ground rover or whatever, to the vehicle that's moving, and it then applies subtracts those errors from its what's called pseudo ranges, which is the ranges that it's got from just the measurement of the timing of from the difference in the clocks from each satellite and its clock on the ground, its corrected clock on the ground. Then the rover performs normal triangulation with those corrected ranges, and it ends up with a better estimate of its position. So how much can you expect it to help? It's actually quite hard to say, because it depends on how much of a contribution the spatially correlated errors is making to your position. If it's all multipath error you've got, it doesn't help much, but if it's primarily ionospheric errors in the estimate of the atmospheric conditions, the ionospheric conditions, then it can help a lot. The estimate we've got from talking to engineers at U-Blocks is that we would expect it to give sort of 50 to 70% reduction in horizontal errors, which is in the ballpark of what we observe. And we'll show some of the results later. And in particular, what we're taking advantage of is that these low-end cheap GPSs actually support injecting the differential corrections directly in the protocol using a protocol called RTCM v2. And they support that. So that means that we don't have to have an additional CPU sitting on this box to do the corrections itself. We can just send up these really tiny packets, like 100-byte packets, every second or so, every couple of seconds, to the rover, and it will then do all the maths inside the GPS to apply those corrections. We've just got to supply it with the corrections in the crazy format that it uses. So this is where I'll hand over to Ben, who will talk a bit about the maths of getting this right.
Yeah, so there have been two real enablers for this technology, two real driving forces behind now being the right time for it. Quite recently, cheap GPS receivers have started to get the ability to receive differential GPS corrections. As Tridge just said. This has been pushed by various clients of the big GPS manufacturers saying, look, we've got these sources of correction, we've paid $10,000 for one receiver that can generate these corrections well. We now want to share some of that high accuracy information across some cheaper receivers. Can you help us out? Because it's only driven by a small number of clients, the use of these RTCM corrections on cheap receivers is still a little buggy, and there are a couple of features that we have found that are turned off or missing as soon as you actually start giving these receivers correction information. The other thing that has recently become available are raw receivers, which are things like this one or like the 6P that Tridge held up before, that have the ability to actually give you not just a position as output, but all of the raw pseudo-range information, and for that matter, the underlying carrier phase information, some better information about the satellite qualities, Doppler shifts and various other bits and pieces. All the raw numbers that you need to actually do the maths. Now this is probably the only part of the system that anyone with a rover or any kind of hobbyist experience in this area won't already have in their shed. And actually they're relatively cheap. They're sub $100 easily. Now it is a case of the manufacturer charging you 3 times as much for a device that does half as much work, right? It just gives you these partial results halfway through and they charge you more money for it. That's still okay. It's still well within the budgets that we have set for ourselves, and importantly, you only need one of these to drive all of the corrections for all of the rovers in a local area. Now, me, myself, I like flying 10 or 15 quad rotors at a time without them crashing into each other. I can use unmodified quad rotors, and for less than $100 using this system, all of a sudden, we can get the collision avoidance that we need. So these give you, as I say, the raw outputs, and I'll just reiterate that it's important that they give the pseudo-range outputs, not the range outputs. Now, what's the difference there? It's just that, as Tridge mentioned, GPS has to solve for time as well. So these measurements that you get from the satellites tell you how far away from the satellites you are in space, but also how far away you are from the satellites in time, how different your clocks are, and that's where the pseudo prefix sort of comes in there. Now, if we need to generate these corrections ourselves, we need to know the position of the reference station so that we have something to compare the incoming measurements to. We can know its position quite accurately. Now, this might be by just averaging the position of the GPS over several days. It might be by surveying it in using proper survey equipment. Might be by using an offline processing tool like the RTK-lib that was mentioned earlier. But somehow or other we can find where our reference station antenna is, where we put it down. What we can't work out is when it is. We can't say that our system is perfectly synchronized to the GPS system time, not without having an atomic clock, which puts us a little bit outside the budget again. So what we need to do is to take these pseudo-range measurements and say, okay, I know where I am, so I don't need to solve for 4 different parameters anymore. I only need to solve for 1. I still need to solve for how different my clock is relative to the GPS time. And it turns out that the estimation of this clock error of your local receiver is pretty much the biggest remaining error in the system. And the inaccuracy in when you are contributes a lot to the accuracy of the final differential GPS solution. Once you've estimated this clock error, you can subtract it from the pseudo range and you get an estimate of the range, just the distance to the satellite. If you know where the satellite is, you get the error, essentially. Now, quick aside here, the GPS satellites are sitting about 20,000 kilometers away from us, and they're pegging around the Earth at something like 14,000 kilometers an hour. And what we want to do is say, right, now, where are you? To within a couple of centimeters. And we can do that, and I think that's actually quite an amazing feat of engineering over the last several years. Once we've got the errors, then we can encode them in a format that's understood by the receivers. This is RTCM V2 in this case. RTCM is just the name of a standards authority that governs maritime radio transmissions, actually, because differential GPS is used a lot for guiding large ships into harbour, essentially. The RTCM V2 format is modelled after the actual on-air format of the satellite data, and as such, it really can trace its roots well back into the 70s, which in turn means that it's fairly horrendous to work with. We have 30-bit data words, not 32, 30-bit data words, 6 bits of which are parity, 24 bits of data. The 6 bits of parity can't be calculated just over the preceding 24 bits of data that they protect, but that parity also depends on the parity state of the previous packet. So if you come in halfway through a stream, you actually have to test all possible combinations of the parity state of the previous packet to work out whether your current one is valid. This is ugly code, as you can imagine, and if any of you have more interest in it, please look at our GitHub and please forgive us for the atrocities that you find therein, but it now works pretty well. Okay. We pack all this stuff together and we can just feed it straight into the serial port on the low-cost receivers, and they take care of the rest. Now, the RTCM V2 format encapsulates the corrections directly, and also a couple of other bits and pieces, but essentially you give it the errors that you've observed. But we're not the only people generating these kind of reference information. Geoscience Australia has a network of about 150 continuously operating reference stations, or cores, around Australia, and about 30 of those are free to use for non-profit if you ask nicely. They're not trying to protect the data, but they don't really have a big enough server to just give out the passwords for free. So you ask nicely and you get access to, as I say, about 30 reference stations around Australia. Luckily, 3 of those are in Canberra, where we've done most of our testing. 2 of them are in Perth, where we've done the rest of our testing. So we're in pretty good shape there. This is one of the reference stations up on top of Mount Stromlo, which is an old observatory in Canberra. That's just the antenna that you see there. It looks a little bit like a Mayan pyramid, but the idea is that it rejects all of the multipath, all of the reflections off the ground get caught up in that structure, in the choke ring. That antenna by itself costs significantly more than our total investment in all of the equipment that we've ever actually bought for this, and is a substantial reason why Geoscience Australia references are quite good, and one of the problems with ours, mostly quite good, and we'll come to that, and one of the things that we're hoping we don't have to worry about too much. Turns out we do, but we'll see that shortly. The other thing to note in this photo, contrast is a little bit low, but there's one reference station here, and actually that guy up there is a second reference station. So we can, in this particular case, compare the corrections on a really short baseline and do some sanity checks. Turns out those sanity checks fail. One of those reference stations, it reports its true position, and while everyone at Geoscience Australia went off for their Christmas holidays, it started reporting its reference position 80 metres down the road. Couldn't work out what was wrong with our code, and it wasn't our code, which is a nice feeling in the end, I suppose. Anyway, the corrections come from Geoscience Australia, not in RTCM V2, which we could give straight to our receivers, but in version 3, which is much nicer. Essentially, the spatial sort of reference community yelled at the standards body, why are you building this standard to be so hard to program? Version 3 is just a very simple, packed, bitwise protocol, no problems at all. It in turn is encapsulated in ntrip, which is really just an HTTP GET statement, and instead of getting a web page, you get correction data. It doesn't provide the corrections by themselves, though. What it provides is just a set of observations. It gives you the raw pseudo range and carrier phase and all those sorts of things. But critically, these have been corrected for the clock error. This reference station knows where it is, but it does actually also know when it is as well, and corrects these pseudo ranges. So what you're getting back are really high quality ranges, spatial ranges, to the satellites. You can do the same kind of differencing that we've done for the local corrections, and essentially run these measurements through exactly the same pipeline as the measurements that we would get straight out of a raw receiver. This turned out to be quite nice, actually. Once we unpacked the RTCM v3 stream, we kind of got all the rest of the infrastructure for free by doing the local corrections. So then we came to test it. First of all, Tridge put 3 receivers up on his roof in Canberra. Later on, he put me up on his roof in Canberra, and then the photograph was taken. Up on the roof there, we have 1 receiver that's capable of generating raw observations, and therefore we can use to generate corrections. 2 receivers that are able to be corrected. We would only correct 1 at a time, so we had a control. Later on, we discovered some problems with that setup and moved to another setup out at Spring Valley Farm, which is a farm owned by the Australian National University just outside of Canberra. A little bit of a hill in the middle that we could stick antennas on that weren't going to be affected too badly by multipath effects. What they were badly affected by was spiders, but that's all right. You just go out there with a shoe, knock them off, and you're pretty well sorted. That's the spider there. The contrast isn't great, but there is a spider on our little laptop there. Yeah. So from the rooftop system, how did we do? What we're seeing here is 3 days worth of data. X-axis time, and the Y-axis, unfortunately, is how much we're correcting the system, how much better our system is than the control, where red is we're making things worse. There's a lot of red there. There's a lot of red there. One interesting thing to note apart from the amount of red there is that it's very well correlated across days. All right? The same kind of errors happen every single day. The other thing that repeats every day is the position of the satellites in the sky. So we can turn around and say, okay, something about our system is breaking badly when the satellites are in a particular orientation up in the sky. What is that? Turns out to be multipath. And if we've got enough time, we've got a couple of bonus slides at the end in which I can go through that in a bit more detail. But the bottom line is that in suburban Canberra with trees about, with other reflective roofs at funny angles, we would have a situation where the reference receiver might lock on to the signal directly from the satellite, and the roving receiver would lock on to the same satellite signal that had been bounced off something, and they would disagree by potentially tens of meters and push the solved system right out into the weeds. Yes, Hugh.
Is that local time or UTC you recall?
That's local time. That's local time in Canberra, yes.
What's the units of the y-axis?
Meters. Yeah, difference in meters. So you can see that through this period we're making things worse by around 5 meters, okay, which is not what we want. Once we narrowed it down to some kind of multipath issue, we had the option of either buying an expensive antenna that could reject multipath for both of our GPS modules, or just moving out into the bush a little way. That's when we set up the facility at Spring Valley Farm. And out there things were quite a bit better. What we're seeing here is the difference in position between each one of our receivers, corrected and uncorrected, with respect to ground truth, or at least as near to ground truth as we could reliably estimate from a combination of a couple of different sources. The red line there shows the distance away that the uncorrected GPS thought it was from the reference position, and overall it was off by about 6 meters-ish most of the time with a lot of variation. The corrected receiver didn't quite get the sort of 1 meter accuracy that we were hoping for, but it sat around 2 meters for the most part, which was good enough for us. Every now and then it does still wander out into the weeds. Once again, this looks to be a multipath issue, perhaps off a farm shed or something similar. I said at the beginning that the cheap receivers do tend to turn off a bunch of extra features as soon as you start giving them corrections. And one of those features turns out to be multipath suppression, which is responsible for pretty much all of the errors that we see here. After we had static tests up on roofs and boxes full of spiders, we actually decided to attach these things to rovers and planes as we needed to, and that's where Tridgell will take over once more.
Right. Unfortunately, with the lights, it's a bit hard to see. That's actually Ben with doing the Ministry of Silly Walks with the rover on his head. Maybe you can demonstrate. So what we have is Ben walking a known path around our local flying field where we go and fly model aircraft. And then we have the ground station. You can actually see in the background there, there's a, well, if we had, there's a little chair and things, that's where we've got the ground station set up, and we have this 6P receiver, and then we have this radio system, you know, way overkill radio system that'll go sort of 80 or 100 kilometres, we're going 20 metres in this case, and it's then sending differential GPS correction packets across using the MAVLink protocol up to the rover on Ben's head, which is then correcting the position. And that allows us to where the ground truth is basically taken by either from the satellite imagery, so basically Google satellite, and assuming the registration of that satellite imagery is correct, which is a big if. And then
a couple more.
For our purposes, the main point of our project isn't, we would like to get really accurate global positions, but if we can just get very accurate relative positions, that is actually, you know, most of what we want. In other words, if we can, because for Ben's project where he's trying to keep the quadcopters away from each other, he just needs each of the quadcopters to get a good relative position from each other. And it doesn't actually mind if the whole position is shifted by 20 metres in latitude or longitude globally. And for a lot of our stuff with planes, it's also true. Oh, sorry? Yeah, please do. Feel free to adjust the lights down a bit.
Press the button that says down lights.
Right.
How many enthusiasts does it take to change the light?
Yeah.
There you go.
Hey.
That's much better. Okay. Right. So, what I'm going to demonstrate to you now, this is, I'll just do a playback. So, as you can see here, this is a satellite view here in Perth. That's the James Oval just outside this lecture theatre. And this is testing we did on Monday morning when we were supposed to be watching the keynote and decided to get a last minute testing instead. So if I zoom in on that position, then just zoom out a little bit there, and then I start this playback. This will play back our log of, and the white line is the line, we had a very kind groundskeeper at the James Oval who walked up to us with a long tape measure, and we triangulated the positions of these ones versus this clock tower here and the corners of these buildings on the satellite imagery, measured out with a 60 metre tape, 100 metre tape, you know, to measure the corners and get this path, which we then put markers with wallets and coins and things for Ben to walk. So if you saw people doing silly things on the Oval on Monday morning, that was us.
Yep.
And so what we're seeing here now is the two paths of the rover, one of which is the corrected positioning, which is, can you guess which one is the corrected one?
Hey.
So you sort of go red, yes. Anyway, the green one is the corrected position walking along this path, and the red one is the uncorrected, luckily. And as you can see, the green one for most of the path around here is giving a substantially better estimate of the position relative to our tape measured position on the oval versus the uncorrected. There are
to be getting better horizontal than vertical.
Oh yeah, it's not perfect by no means.
But I mean 1x.
Yeah, and there's actually a really interesting reason for that we'll come back to at the end of the talk if we've got time.
Yeah. So there's, you can notice there's some places where it's not so great. You know, you see that little dog leg that the corrected one did at the beginning. And you can see that there's a little bit of error down here, sort of 1.5 meters or so. This is great. We're delighted with that. The scale here is sort of 20 odd meters there to there. So that's sort of scale. But overall we were pretty pleased with that. We were puzzled for a while though, because the corrected GPS was claiming that we were at an altitude of 35 meters. And the SRTM data from NASA shows this as being about 9 meters. We were rather puzzled by the results. We actually this is for one of our tests where we're using the N-trip data, the N-trip reference station on the coast, 19 kilometres away at Perth. Then we looked up the position of that N-trip reference station, its own claimed position. It's perfectly, position that Geoscience Australia gives, and it claimed to be 25 metres underwater. And that's left us with a slight puzzle. We think that there may be some difference in the datum that's being used. It's not quite right, and we're still to work out exactly. So there must be some transition from ECEF to latitude, longitude, altitude, LLH positions, and we're still haven't got quite to the bottom of that because we thought we were using the same datum as they were, but obviously not. Either that or they just haven't realised that they're flooded. Not sure. Anyway, so that's the result there, and but generally fairly happy with it. We've also done flights where we've flown it in a small aircraft. This is a test flight where we were flying a Skywalker 2013. It's basically a 1.8 metre foam glider, electric glider, again running the dual GPS and now the little APM autopilot. And this is zoomed in on one part of the flight path where it's going around a corner here, and the green here is the corrected position, the purple is the uncorrected position. The problem with testing an aircraft is it's very hard to get a truth position, to know really where it is. You can't judge it by eye. Positioning sensors that will accurately measure the position of an aircraft in the sky are horrendously expensive and generally far too short range for the sort of flying that we're doing. So it's good to see that it's working and that the plane doesn't actually fly off over the Brindabellas, but it is much easier to do to test the accuracy of the system using something like this, where you can see exactly where it is on the ground, which is why we're concentrating on rovers initially. Also because there's a rover competition that we're in the States where very accurate positioning is key to that competition. So of course we're trying to do well in that competition. So that's the results on a small Skywalker. Then there are some other low-cost options that are possible that I thought you mentioned. One very exciting one at the moment is the SwiftNav Pixie, a Kickstarter that kicked off a few months ago and that we've put our name down for. We hope to have one of them here before the conference, but unfortunately, with the way Kickstarters go, it hadn't quite got here by then. It is a around $500 per module GPS. You'll need 2 of them, so it's sort of a $1,000 solution. Or if you have like 10 multicopters, you'd need 11 of them, so it gets fairly pricey. It's got an STM32 on it with open source code that does a full RTK, so real-time kinematics, so it's doing the disambiguation and all of the fancier maths involved in using the phase information from the signal. And they hope to get down to decimeter type accuracy, which that is a price point for decimeter accuracy that is well below anything else we've ever seen, which is great. And it's very compact. It's roughly the same size as one of these GPS receivers, due to the wonder of the great little STM32 processor. Unfortunately, it's got an FPGA on it, and the correlators, that sort of thing. That isn't open source, unfortunately, but all the higher level software stack is. Looks very promising. RTK Lead is the other one that's been around for a while that I mentioned towards the start of the talk, and you can pair that with something like a Raspberry Pi or a BeagleBone to get potentially decimeter-like accuracy. We've yet to see a really convincing demonstration that will work in the types of applications that we have, plus it requires that you have substantial CPU power on the rover, which is not really what we wanted to do with this project. We wanted to be able to have the single low-cost GPS module on the moving vehicle rather than having to augment it with a fast gigahertz class CPU running Linux. So that's other low-cost options that are possible. So we'll now just do conclusions. Then we've got some bonus slides, as Ben mentioned, or open the floor to questions about the system.
Yeah, not much time for that, but
yeah,
that's all
not
right.
much time. So basically, we've got like 5 minutes or so.
Yeah, we've got a few minutes.
A few more minutes. Okay. So our conclusion is that it is possible to get better relative positioning, and I stress relative, not absolute positioning, using cheap differential GPS and RTCM v2 injection with not massively complex and now available code that can take raw corrections from a relatively cheap receiver like this, and to create correction packets which will be accepted by these cheap receivers to correct their position. Getting a good reference position is hard, really hard. If we thought we could just use registration of Google Satellite, that sort of thing, or Microsoft Satellite, but if you look at different months of their satellite, here at James Oval, for example, if you look from the images from 3 months ago versus now, you see several meters of shift in the registration of their images. Which is correct? We don't know. You need a survey quality GPS to know. Other options are the Pixie, which will open up some great options. Altitude is still poor even with DGPS, although part of that is problems with the datum, as we mentioned, with NTRIP solutions. So landing with a GPS still isn't quite there as far as getting the correct altitude to flare the aircraft as you're bringing it in. Okay, so open up the floor to questions.
Just one moment. Just from everyone here at LCA, we'd like to thank both Tridge and Ben. We have some wonderful complimentary towels here for both of you.
Oh, thank you.
Thank you very much.
There you are.
Thank you.
And we will be breaking up for lunch soon, but there is enough time for us to have a couple of questions. So,
Okay.
Have you considered adding non-GPS sources of information? So, for example, altitude for location, or really just optical beacons that you could measure randomly?
So the question was, have we considered using additional sources of information for position that can augment it for so various RF solutions or laser solutions, etc. For altitude, yes, we have. We've done experiments with sonar, for example, and we're looking at LED and laser-based altitude solutions. Positioning, we haven't tried any, or Ben has done RF systems in small distances. He's got, but they're relatively expensive, sort of $35,000 type systems. The other option is to combine the GPS information with the other sensors like the accelerometers, the gyroscopes, the barometer, etc., into something like a Kalman filter, and to produce a better solution, which in particular may give a better kinematic solution combined with something like the SwiftNav Pixie. And so, yes, we're looking forward to that possibility. We're just switching across to a Kalman filter now in our attitude, and it is certainly very likely that we can combine sensor information for attitude to reduce the ambiguity that a RTK system produces in its position to get a much more accurate position, particularly in highly dynamic movement where you're doing loops and rolls and that sort of thing. Yep.
How quickly is the correction data changing? Because there's obviously latency in transmitting the
Right.
correction data from the...
So the question is how quickly is the correction data changing? There's short-term jitter on the order of tenths of a second type thing.
Yeah, about that.
And then there's longer-term changes which are at the order of many tens of seconds. We're not caring about the really short-term jitter. In fact, we do some smoothing and things over to get rid of that. And we transmit typically at 1 hertz, 2 hertz, 4 hertz, that sort of scale, depending on how much radio bandwidth we can afford. The system then reports the age of the data, and we're typically seeing ages of the data that the receiver is reporting of the order of 2 to 5 seconds, depending on the communication of our radio, etc. But usually, a second or two. Yep.
Do you choose the jitter to ignore based on a solution that says that it's okay, or just that you can't handle it because it's too hard?
Primarily, we can't handle it, but we just do some smoothing, and we actually smooth the data over relatively long time periods, tens of seconds. And depending on which one, we also apply, for the local positioning, apply a hatch filter, which is a filter that's based on the phase information that you get out of the raw signal, and it tries to detect when the receiver has lost lock with the signal, with the phase of the signal. And that's a standard filter. This guy, Hatch, invented this filter that is a mechanism for smoothing pseudo ranges based on the carrier phase information you get from GPSs. And so we apply that standardized technique in our code as well.
one or two more questions and then we'll probably wrap up.
Okay.
Sorry, can I just take your earlier question now about the north-south errors? Because I quite like the answer to this one, and sorry, we'll get to one in the end. So the question earlier was that on the test in Perth, it was quite obvious that we had much better positioning east-west than we did north-south. And if we had a three-dimensional plot, you would actually see that our error in altitude was worse again. And the reason for that, you might remember I said that the major residual source of error with our raw receivers is to do with the clock error. We don't know exactly when our reference receiver is. So we end up with this error that's common to all of the satellites because of our clock error. If the error is common to all of the satellites, and the satellites are primarily above you, then most of that error is going to translate into altitude, right? All these ranges coming down from the satellites are going to mainly pull you up and down pretty much on a line. The second order effect, though, is the fact that we're in the southern hemisphere. So most of the satellites are to our north. So this common mode error actually affects the north-south accuracy much more than the east-west because, as I say, we have roughly equal numbers of satellites east-west, but north-south, they're very much biased up towards the north. So that's where that bias comes from, I suppose. Okay. Is there one last up there?
How quickly does the correlation decrease given distance from your reference point?
That's actually a really good question. We haven't done a lot of experimentation over long baselines. How much does the correction information vary over distance from your reference position? Yeah, sorry, thanks. So, as I say, we haven't done tests over long baseline because the point of this is to essentially have everything in your ground station. The sort of standard response to that is that for single frequency corrections like this, you want to be within about 10 or 20 kilometers. Dual frequency corrections is more like 50 kilometers. So yeah, using the reference station 20 kilometers out up the bay here is probably on the edge of being good quality. Yeah, these local ones we really want to keep within no more than 10 kilometers. Yeah.
Have you explored using different GPS systems?
Yes, we have. We've tried a number of different GPS modules. We tried, for example, the Skytrack Venus ones, and it was awful.
The Chinese.
The Galileo and the Beidou and all these sort of ones. Yeah. No, we haven't tried differential GPS with those. Part of the problem is that we don't have cheap modules that do those satellite systems and accept differential corrections for them. So if that became available, it'd be interesting. But some of the GPSs that support these additional systems, they add that as a feature to say, hey, we support all these systems, and people assume that means they're better, but they actually might be rotten receivers. So just because a receiver claims to be 50 hertz and support every satellite in the sky doesn't mean it actually produces a good position. So we've kept coming back to the U blocks because they seem to know what they're doing.
All right. One last question. And then
Yep.
The corrections that you broadcast are potentially available to anybody with a receiver in your 50-kilometre region, aren't they?
Oh, we could if we had the bandwidth to distribute them. So the question was, our corrections that we create, they're potentially available to anyone in a 50-kilometre region. Yes, we could announce them, and we could even have a little, ham radio set up that puts out the corrections. You could, but OpenStreetMap tends not to worry about sort of 5-metre errors, I think, mostly when they're doing hot type stuff, because, if they're trying to find a flood or a disaster, if you're within 5 metres, you can probably find it. But still, yeah, you could create a broadcast station. You could create your own in-trip network, indeed.
thank you for your time, Tridgell and Ben.